Hello everybody, today I'm going to talk about light, specifically about light's properties. Light is both a wave and a particle. I'm going to talk about that. So firstly, I'm going to talk about light's wave properties. The fact that light is a wave. This was proven by Thomas Young, was it? It was proven using the double slit experiment. So, well, what the double slit experiment is we have a thingy shooter. It shoots particles or waves, and there's a thingy catcher, and this thing catches the stuff that this thing shoots. And so let's say this thingy is shooting some baseballs at the thingy catcher, and it would shoot, and it would catch in the area where it landed on the thingy catcher. And if it were to shoot like that, the thingy catcher would keep the baseball over here. And so now we're gonna think of a thingy in the middle, which has two holes in it. Those are the two slits, the double slits. And now we're still gonna imagine some baseballs shooting out of the thing shooter. If the thing shooter is gonna shoot baseballs and make it land on the thing catcher, the baseballs that go through would go like that and land on somewhere around here or there. And if we make a graph over here of where the baseball landed, it would look a little bit like this. Yeah, no probabilities on the other sides, but very high probabilities, or all of the probabilities on the spot where the slit made the baseball go to. It would look a bit like that. But now we're gonna think of waves. We have the two slits, and we're gonna shoot waves through this thing. The thingy shooter is gonna shoot waves through this thing, and the waves are gonna be water. And there's a better way to think about this than the two slits. It is putting two thingies in the water and shaking it simultaneously, and it would create water waves, and it will interfere with each other and make cool shapes. But because it is too hard to draw, I recommend the video over there. It is by Veritasium, and it's a very interesting video. As you can see from that video, you can see that if we have a tub of water and we shake two stuffs, where the water is staying flat because of the low side of the water and the high side of the water wave interferes and makes a flat place. Because of that, the wavy part of the water gets separated a little bit and stays there, like some wavy part here, no wavy part here, wavy part there, no wavy part there, and wavy part there, and so on. Something like that. These shapes get made if you get two waves interfere with each other. And the double split experiment, and from the experiment that Thomas Young did in the early 1800s, he used sunlight and made the sunlight go to two very small slits, a separate hole where you can see through the box, inside the box where the two slits or on the outside. He made a hole to see how the light got separated or whatever, and he saw that, and he saw light being like the size of the circles represent the brightness of the light. He saw this pattern where the light got separated, like how it was a wave, like you saw from the water. So light separated like that. So therefore he proved that light was wave. Light was a wave. So now if you draw a graph, the probability of light would be something like that. Very blobby and jelly-ish. And now, but about 100 years later, Einstein did an experiment. It was the experiment about the photoelectric effect. And what the photoelectric effect is? Well, this one, the double slit experiment proved that light was a wave, but now the experiment on the photoelectric effect proved that light was a particle. Now we're gonna use a electroscope, which is a device where you can see how much electrons are, where you can measure electricity, kinda static electricity. It looks something like this. So there's this big rod going through the middle, and there's this needle stuck inside the middle where it can rotate freely, and it is all made out of metal, and the top part is also metal. And if the top part is charged with electrons, negative electricity, so basically you rub a balloon on your hair and get some electrons on the balloon, and then scrub the balloon on the metal plate to get the electrons off of the balloon and onto that metal plate. And and through the metal rod and the metal needle, the electron moves, and now it is the rod and the needle is all charged negatively. So because of the electromagnetic force, the needle moves because of the pushing force of the electromagnetic force. And if you put your hand on the metal plate when it is negatively charged, the electrons from your electrons in the metal needle and the rod and stuff goes onto your hand, and it discharges the whole thing, the whole electroscope, and the needle goes back into its own place. And now here's the thing: when it is negatively charged like that, let's say this is a flashlight, a very poorly drawn flashlight, but now we shine flashlight onto the electroscope, and well, light can release electrons from atoms because it has energy. But well, this flashlight is flashing white light, which is red light, blue light, and green light combined, which are visible lights. And the visible lights, no matter how much visible light you shine on the metal plate part of the electroscope, the electrons aren't getting released. No matter if it's 1,000 lumens, 10,000 lumens, or a trillion lumens of visible light, it won't make the electrons get popped out of the atoms and release it. And using that method, releasing some electrons inside the electroscope, and by therefore resetting, discharging the electroscope. But it can't do that, whether if it's, as I said, a million or a billion or a trillion lumens of visible light. But now we're gonna think of some long-wave ultraviolet lights, which are the ultraviolet lights which make your skin get sunburned. And now this ultraviolet light, this long-wave ultraviolet light, has more energy than the visible lights. So now we're gonna think of this flashlight as shooting, as if it's shooting some long-wave ultraviolet lights. This light will soon discharge the electroscope and make it look like this again. And now this doesn't matter if it's a very strong long-wave ultraviolet lights or very weak long-wave ultraviolet lights. No matter the strength, if it is long-wave ultraviolet lights, the electroscope will still discharge, but, well, depending on the strength, the speed will vary. And now we can see that something is a little bit weird about this light being a light having wave properties, because let's say this is visible light, the wave of the visible light, and this is a wave of the long-wave ultraviolet lights, and it is shorter, and therefore having more energy. But we can also give the visible light more energy by just increasing the strength and making it look a little bit like this. Even though it is, kind of squished, but even though it is still visible light, there we go, we fixed the drawing because it was kind of bothering me. But now it is still visible light, but it has more energy because it has a stronger strength. And no matter the strength of the wave of the visible lights, we couldn't get the electron to pop out. But the ultraviolet lights, even if it had weaker strength, it would still discharge it and make the electrons released. So how could that be so? And this doesn't make any sense if it was a wave, because it has the same strength. But now we can imagine as particles. And if it was a particle, it would mean that increasing the strength of the light being the same as just shooting more photons at the same time. But a single atom can only get hit by one photon at a time. And so if the question of does the electron get released matters about the strength of one photon, but increasing the strength on the visible light would mean just more weak photons, but that won't do the trick. But the long-wave ultraviolet lights, these have a lot more energy stored on one photon, and so this photon, when it hits the metal plate, this photon has the ability to make the electron get released. So Therefore, in this case, the light being a particle makes much more sense. But also the double slit experiment wasn't wrong. So now we can say that light has both properties of particle and wave. And also, if you look on the internet and search for the meaning of a particle, it would say the smallest vibration on a quantum field. That statement basically states that particles are waves, and waves could be particles. And so the photon is the smallest vibration on a electromagnetic field, and a quark is the smallest vibration of the quark field, and it works like that. And ultraviolet light is, its wavelength is so short we could just imagine it as a straight line. Its wavelength is so short, the vibration happens so quickly, we can just imagine as a line, and as like if it was more like a particle. But infrared lights or radio